In this lesson, we're going to learn how to incorporate multiple bonds into Lewis structures. You may recall the rules for drawing Lewis structures. You have to, number one, you have to identify a central atom. You then have to count the valence. Once you know how many valence electrons you're dealing with, you then have to always try a single bond between the central and the surrounding atoms first. So you have to identify the central. You then need to count the valence, and we always try a single bond between the central and the surrounding atoms. Then we give the surrounding atoms an octet. We make sure that they have 8 by adding in lone pairs. Then if you have any extra electrons, they always get to go on the central atom. We're going to see in the example for this presentation that the central atom is not going to have the octet that it needs. That is, there's not going to be any extra electrons to add to that central atom. And we say that that central atom is electron deficient. So we're going to learn how to incorporate multiple bonds into Lewis structures. We're going to use HCN as our example. In this case, usually the first element in the series would be your central atom. Hydrogen cannot be the central atom. That's why we're given that carbon here is. Hydrogen is an exception to the octet rule. Hydrogen can be stable with only 2. It's trying to emulate the noble gas helium, which is stable with 2 electrons. So we're going to let carbon be our central atom here. So we've identified our central atom. Notice the next thing that we're going to accomplish is we're going to count the valence. And hydrogen being in group 1A gives us a valence of 1. Carbon is in group 4A, so it provides a valence of 4. And nitrogen is in group 5A. So if you add up the total, we have 10 electrons here to try and draw our Lewis structure. The next thing you always want to try is a single bond between the central and the surrounding atoms. So what you see in front of you is a single bond between the hydrogen and the carbon, and a single bond between the carbon and the nitrogen. So at this point, of the 10 electrons that we have already used 4. Because you may remember that each line represents a sharing of 2 electrons. The next thing we need to do is make sure that the surrounding atoms have an octet. We're not going to have to worry about hydrogen on the left because it's already stable with 2. So we're going to need to add some lone pairs around the nitrogen on the right. So we're going to add in our lone pairs for the nitrogen. And notice we get to add in 3 lone pairs. And nitrogen now has the octet that it needs. It now has 8 electrons. If you count the 6 electrons within the lone pairs, each dot represents an electron, and then the 2 that are being shared between the carbon and the nitrogen. If you count all of the electrons we've used so far, we've already used all 10. So hydrogen's stable on the left with 2, nitrogen stable on the right with 8. If you ever have any extra electrons, they always get to go on the central atom. In this case, we've used all of our valence electrons. There are no extra electrons to go on the carbon. Carbon is not an exception to the octet rule. Carbon does need 8 electrons around it. So what we like to say at this point is that carbon here is electron deficient. Carbon doesn't have the 8 electrons that it needs. Whenever you have a central atom that is electron deficient, we now have permission to try a multiple bond. So now we're going to incorporate in a double bond into this Lewis structure. We're not going to put one on the left-hand side between the hydrogen and carbon because hydrogen only needs 2, and of course that would give it 4 if we incorporated a double bond there. So we're going to try a double bond between the carbon and the nitrogen, and that would be 2 lines instead of 1. And this will now be the sharing of 4 electrons instead of the sharing of 2. Anytime you incorporate in a double bond, you're going to reduce the lone pairs down. So currently you see in front of you for the single bond, nitrogen has 3 lone pairs. When we incorporate a double bond, that's going to go down to 2 lone pairs. So let's change that single bond between carbon and nitrogen. Let's change that to a double bond. You now notice that the lone pairs went from 3 lone pairs down to 2 once we incorporated that double bond with the carbon. Nitrogen still has the octet that it needs. It has the 4 that are being shared, and it's got the 4 electrons within the lone pairs. Hydrogen's still good over there with its 2 electrons. And carbon now in the center, it needs 8. And notice by incorporating a double bond, it now has 6 around it. It's got 4 on the right hand side and 2 on the left. So carbon here, even though we incorporated a double bond between that carbon and nitrogen, Carbon here in the center is still electron deficient, still doesn't have the 8 that it needs. So now we're going to have to go to the maximum in bonding, and that would be a triple bond. So we're going to change that double bond between the carbon and nitrogen to a triple bond, 3 lines, which would be the sharing of 6 electrons. Each line is symbolic of the sharing of 2 electrons. When we do this, when we change that double bond to a triple bond, we're going to reduce the lone pairs on nitrogen down to 1 lone pair. So every time you incorporate another bond between things, you have to make sure the lone pairs gets reduced down by 1. So let's change that double bond now to a triple bond between the carbon and nitrogen. So once we incorporate this triple bond, now see the lone pairs on nitrogen has been reduced down to just 1 lone pair. And now if we go back and check to make sure everything is stable, hydrogen still has the 2 that it needs. Nitrogen does have 8. It is sharing 6 with the carbon, but it's still got the extra 2 electrons in that lone pair for a total of 8. And now carbon in the center now has 8 electrons as well. So this would be the proper Lewis structure for HCN.